So suppose you have two functions that are 2-pi periodic continuous with the same Fourier coefficient, and I want to say that the functions are the same. Well, let's start the proof of this. Well, there's a very standard way of approaching this is we look at differences of functions. H equals f minus g. Now, if you take the Fourier coefficient, well, what is the Fourier coefficient? It's f minus g inner product with en. Everything here is linear. The integral expressions are linear. So this is f hat n minus g hat n. The f hat n comes from f inner product with gn, and then minus g inner product with en. So minus g hat n. But these were presumed to be equal. So now we have a function that is continuous, 2-pi periodic, and has Fourier coefficients equal to 0. So we want to conclude that it's actually equal to 0. And how we will show that is actually we will use that lemma, is that we want to actually show that the L2 integral, or the squared integral of the function, is equal to 0, because then by lemma, h is equal to 0. So let's prove this claim. And okay. So we will use the approximation theorem here. So the idea is to write this as a product of two things, h and h and h bar, and to approximate one of these by a trigonometric polynomial. Because then we get a product with a trigonometric polynomial, and we can split it up into terms that we can manage that will involve the Fourier coefficients. Okay, so let's fix epsilon 1 over n for each n in natural numbers. Then there exists by theorem, by Weierstrass, there exists hn in trigonometric polynomials. That is, they can be written as a sum of e to the ik theta. Okay, there's a bit of an indexing mess here because each n has different coefficients. So there's be a double index akn, the kth coefficient of the n one, and they can have different numbers of coefficients. In general, the coefficients would go off to infinity. So m cat subscript n is which coefficients are included. Some of these are allowed to be 0. There's probably no preclusion of that. Okay. So, but then we have that the largest difference between the functions is less than epsilon, which is now 1 over n. So we're applying this with different epsilons, just like we do often with these sequential things. And what do we get? We get a sequence of functions, hn. And we showed that this claim here exactly is saying that the hns converge uniformly to h. Okay, so now we have a sequence of trigonometric polynomials converging uniformly to the function h. Okay, now a small remark is that h is bounded because we have a continuous function and it's 2-pi periodic.
Can you just replace repeat the soup part up there that you had? I didn't hear what you said about
that. This part here?
Yeah.
So well, maybe I'll just clarify this. I'll write this a little bit differently, that will maybe make it clearer. So, since we didn't use this notation so much, what this means, the soup being less than epsilon, is saying that for every x, hn of x minus h of x is less than or equal to epsilon, which by our choice is 1 over n. But this means that hn of x is converging uniformly to h, because all you have to do is if you want to make if you want to make the difference less than epsilon for all x, well, you choose the n accordingly. Epsilon n should be. So this is saying that you can make the difference less than 1 over n. Now, if you fix an epsilon, you can make this difference less than epsilon by choosing n bigger than 1 over epsilon. Did that clarify, Elijah?
Yeah, that's good. Thanks.
Yeah. So what this Weierstrass is really giving us is a sequence of things that converge uniformly once you unravel the quantifiers a little bit. Okay. Now, we also know that the function h is bounded. I mean, this is not completely automatic, but we can use first boundedness on 0 to pi. And why is that? Because h is continuous and 0 to pi is compact. But then we have to add a 2 pi periodicity to extend it to everywhere. That saying that h as a function from r to r is bounded. And r is not compact, so it can't just say that function is bounded. But 2 pi periodic continuous functions are always bounded because the values only depend on 0 to 2 pi. You can translate any other point to be in that interval. Okay. But then there's a small exercise, and where do we need this boundedness? Well, we need to show, we want to talk about hn bar. Well, hn converges uniformly to h. So if you look at h times hn bar, this converges uniformly to h bar. Without the first factor, this is relatively easy because if you look at the difference between h and h bar, hn and hn bar, this is the same thing as the difference between h and hn. And we know that h and hn are becoming small uniformly. But the issue here is that there's the product by h. But that's not really a big thing. A sketch of that is that by what we just said in this remark, h is bounded. So since we can make difference hn minus h less than epsilon by choosing n, say, equal to ceiling of 1 over epsilon, and we can make h less than m, so then we are less than m times epsilon. So adjusting the choice of epsilon will allow this to prove to work. This is a sketch. I don't want to get, I want to highlight the main themes of this without going into getting too bogged down by the details. Okay, so we get that h times hn bar converges uniformly to h squared. Well, what does that give us then? Well, then, by theorem, we get that integral from 0 to 2 pi of hn bar, so where the function is inside and the limit is outside, is the same thing as taking the limit inside, because this thing here converges uniformly to that. So by theorem on convergence of integrals. We get the first inequality here. But let's compute the left-hand side in a different way. So this is, limit is on the outside. On the inside, we have an integral from 0 to 2 pi, h times this trigonometric polynomial. Well, let's see what we get. So the limit stays on the outside. Don't do anything to the integral. Also, the integral should be h in d theta. But this is now a finite product, so we can take it inside the sum, and we can take the integral inside the sum. So let's use linearity. K equals minus n little n, capital N, little n. When we have a bar here, bar is linear and multiplicative, so it will it will descend into a bar on the AK and give us a minus IK theta there. So we get AK bar. That term won't matter. So even if you forgot the bar, it won't really kill you. So H theta e to the IK theta. Let's actually just leave the bar. We don't need the second rule there. But what is this here? This looks like an inner product. So let's write it as such. K equals minus n little n, capital N little n, AK bar. And there, the only thing missing is a 2 pi factor there. So let's add the factor there. H inner product with EK. But this is equal to 0 by assumption. So everything is equal to 0. So the left-hand side here is equal to 0 in a sense because H is perpendicular to all trigonometric polynomials. Then the right-hand side is also equal to 0. But we concluded by the lemma that once we get that the square is equal to 0, then the function is equal to 0. Now, yeah, it takes a while to fully appreciate this proof. I just will highlight the steps. You look at the difference, f minus g, you want to argue that it's equal to 0. The idea is to look at its square integral, but to approximate it by taking first a sequence of hns converging to h. Then a small argument gives you that h times hn converges uniformly to h squared. And these two sides can be computed in 2 different ways. So one leads, when you take the limit inside, you get h squared. What we want to say is 0. When you take it on the outside and expand everything, you get inner products with basis elements, which are 0. This is actually very important argument.